In this example, we're going to find the eigendecomposition for matrix A. We're going to then compute A cubed using this eigendecomposition. So we know that A minus lambda I for eigenvalues times a vector of variables is equal to 0, right? And so A minus lambda I is going to be 2 minus lambda, 3, 2, 1 minus lambda. Okay, so if we've got this matrix equation, we want to find the values of lambda that that make this work, the eigenvalues. So to find the eigenvalues, we look at the determinant of this A minus lambda I, and we set it equal to 0. So we end up with 2 minus lambda, 1 minus lambda, minus 6 equals 0. So we have lambda squared minus 3 lambda minus 6 equals 0. That's not true. Minus 6 plus 2, so it's minus 4. And so we end up with lambda minus 4 and lambda plus 1 equals 0, which means lambda is going to be 4 or negative 1. Great. When lambda is equal to 4, then plugging it in here, we've got 2 minus 4 is negative 2, then 3, then 2, and then 1 minus 4 is negative 3. And so we end up with 2x equals 3y, or the eigenvector x is equal to 3, y is equal to 2, because that is a solution to that equation. Now we have lambda equals negative 1, and so we get 2 minus 1 is 3, then 3, then 2, and then 1 minus 1 is 2. And so here we've got x equals negative y, which gives us the eigenvector x equals 1 when y equals negative 1. Great. So let's find our P, D, and P inverse, right? We know that we can decompose A into a product of 3 matrices, P, D, and P inverse. Okay, so in this case, P is going to be the matrix with our eigenvectors as columns. So 3, 2, 1, negative 1. D is the diagonal matrix with the eigenvalues on the main diagonal. And P inverse is the inverse of P. So here we've got minus 3 minus another 2 is minus 1/5 times minus 1, minus 1, minus 2, and 3. So we've got our PD and P inverse, and A is equal to those. If you multiply that out, you will in fact find that A is equal to PDP inverse. Now, how do we compute A cubed? Well, A cubed is A times A times A, so it's going to be P, D, P inverse times P D P inverse times P D P inverse. And you'll notice that the P inverse P's in the middle are going to cancel out because their product is the identity. So we end up with a P on the left side. We end up with 3 D's, or D cubed, in the middle, and then a P inverse. Now D is a diagonal matrix, and if you multiply diagonal matrices together, they stay diagonal, and you just exponentiate the diagonal elements. So D cubed, in fact, should be 4 cubed is 64, 0, 0, 1 cubed is -1. So A cubed is going to be the product of P, or D cubed here, and our P inverse, where P is here, P inverse is there, and our D cubed is right there. So in this example, our A cubed, we multiply 3 matrices. Computing A cubed, we would multiply 3 matrices. But you can see here that if we had A to the power of 20 or A to the power of 30, we would simply just take our D and raise that to the power of 20 or 30 or whatever our exponent is. And we do that just by exponentiating the values rather than multiplying entire matrices together. So in this way, we save a ton of time, computational time.